This is Mrs. O'Neill for AP Chemistry, Chapter 14, Section 3, Part 1, Concentration and Rate Laws. You should have watched the intro lesson on the rate law. Here are my notes. So he talked about the breakdown or the decomposition reaction of ammonia into nitrogen and hydrogen. And if we were to graph the concentration of ammonia turning into nitrogen and hydrogen, the rate would form a straight line, which means that reaction rate would be the same all the way through that process. However, sometimes we get a curved line of a reaction. In other words, something like nitrogen dioxide decomposing into nitrogen monoxide and oxygen gas. Well, this curved line tells us that in the beginning, a lot of that NO2 is proceeding very quickly to form products. And at some point in the graph, at the bottom of this curve, there's a little NO2 that is reacting slowly to form those products. So we need to understand that we cannot ever tell how fast a reaction is going to go by just that balanced stoichiometric equation. We have to do it experimentally. So he actually gave us this nice flow chart, as he always does. And of course, this is what we're ultimately trying to figure out. What is our rate law expression? And every reaction has a different rate law expression or a rate law equation. Unfortunately, we have to figure out what those M and N's, which are orders, we have to figure that out experimentally. So that's what we're going to do. The second part of this section, the second video of this section, is going to be dealing with the problems on how to figure out what those M and N numbers are. After that, you can figure out what the K constant is. And then overall, after we figure out the K constant for a reaction, we can give you any concentration of our reactants and figure out how fast or the rate of that reaction will go. So he talked about three different orders: a zero order, a first order, and second order. And then, of course, he went into a little bit more detail. If it's a zero order reaction, the rate actually equals K, which means there's no bearing on the reactant. It doesn't matter how much reactant we have. It doesn't matter the concentration of that reactant. The rate is always the same. So if you notice here in the three experiments, they changed the concentration of our reactant, but the rate always stayed the same. So it's independent. Rate in this particular reaction is independent on how much concentration we start with. The reaction is going to go the same speed. In a first order reaction, however, the rate is going to depend on the concentration of our reactant, usually just one reactant. So as we look here, again, looking at our three experiments with the concentration, as we decrease, in this case, decrease the concentration by 2, what's happening to our rate? It's actually also decreasing by 2. So we can also say that as we double the concentration of our reactant, we're going to double the rate. And again, this gives us our straight line. But notice the straight line is coming from the natural log of that reactant, not just the concentration itself. So if we graph just concentration versus time, we get a curve, and that's really hard to analyze. So we need to change those values to the natural log of concentration to give us our straight line. And that's going to be really important later as far as being able to identify a graph and what order that reaction is according to what is actually being graphed. Second order reaction can be two different ways. One way he talked about is concentration of one reactant squared. And that's one thing we want to understand, is that 2 here, that is an exponent, right? We're not just doubling the concentration, we're actually squaring that concentration, which means we're squaring the rate, okay? So as we double the concentration, we're really squaring the rate. So again, if you notice, if we just graphed regular concentration versus time, we get a curve, and that curve isn't really going to help us. So what happens here is now we're going to graph 1 over, or the inverse of concentration, and we get that nice straight line that's easy to analyze. So again, looking at our three experiments, I'm going to go from 3 to 2 to 1. What happens here from 1 to 2, 2 to 4, we're doubling, and notice the rate, and what's happening to it is we're actually squaring it. So now we can talk about something that is two reactants. Well, if it's two reactants, something like this is also just considered a second order because we take 2 plus 1, B is 0 order, 2 plus 0 is 2. So again, the concentration of B really is irrelevant. We don't have to worry about the concentration of B because it doesn't matter. It doesn't matter what we did with the concentration of B. The rate does not change because of B, but it does change for A. So we really need to know the order of each individual reactant and then, of course, the overall order of the whole reaction. So he wanted you to try for yourself. Hopefully you did. Hopefully you understood and got that A, the concentration of A is first order. The concentration of B is also first order. So overall, 1 plus 1 is 2. So the overall reaction of this reaction is second order. So again, we want to understand that a straight line is going to give us the order of reaction, and that's going to help us when we are just looking at a graph and trying to figure out what is going to help us with that rate of reaction. There's an AP question I've seen in the past where that's what they do. They give you graphs, and you have to be very, very careful as to what is being graphed and which one gives you that straight line. So for instance, if you just graph concentration versus time and get a straight line, it's considered 0 order. If you graph natural log of concentration versus time, it's considered first order. And if you graph 1 over concentration versus time and get that straight line, it's considered second order. So this is going to be really important. And then, of course, he talked about a particular lab. So you should have also watched the intro lesson on the rate constant. So again, here are my notes. So he showed you this rate law expression, rate equals this little k, which is a constant, the concentration in molarity to those exponents. So that is our general formula for rate law. So that the rate constant depends though on temperature and the presence of a catalyst. This is what's a little confusing. We think of a constant as always being the same. Well, a rate constant is the same per reaction. However, that reaction K, that value of K, is not always constant because it's going to depend on the temperature of that reaction and if there's a catalyst involved. So again, that rate constant varies so much between reactions as well as within a reaction. So that rate constant, this little k value, has to be identified, or I should say calculated experimentally. So again, even though it's called a rate constant, it really is not constant because it depends on temperature and if there's a catalyst involved. He also talked about radioactivity and this half-life. So he kind of went through these dots being molecules and things like that, but he also talked about this equation, time 1/2, which is half-life, equals 0.69 over that K constant. That is on your reference sheet and it will be important later. So he talked a little bit about the 0 order versus second order and what that means. Now let's go on to your packet. So in this section, it's going to show you the effect of concentration on rate is expressed quantitatively by rate laws and show how rate laws and rate constants are only determined experimentally. So pause the video. I strongly urge you to write in the blanks as well as read as you write. So read as you're writing those words in. So this rate law is just an expression, and we want to understand that this expression is dependent on only the reactants. That's the first thing to remember, right? Only the reactants play a part in the rate law, as well as the initial rate. Once we mix those reactants to form products, that first few seconds that the reaction happens when you're timing it, that's the rate law is based off of. We want to remember that some reactions are reversible. Those are those equilibrium reactions. Well, we don't want any part of the products to turn back into reactants and be part of that rate law. So that's why we do not include products in our rate law expression. It is only based off of the reactants, and it's based off of when they are initially mixed. So pause the video and read over this. Hopefully this makes sense to you. And we are going to talk about reaction mechanisms later on as well. And reaction mechanism, just real quick, is a step by step how the reaction goes through, because most reactions do not happen in one step as you're used to seeing. So here's our rate law formula as an example. So here's our reaction. We have our reactants, we have our products. So the general formula is rate equals our constant, our rate constant of this reaction, times the concentration of one reactant to some order, which we don't know yet, that exponent, times the concentration of another reactant times again, or I should say, to that exponent n. And we want to remember that these orders is how dependent the rate is according to that reactant. So just like we saw in Mr. Anderson, when that B was a zero order, that meant that B had no bearing on the reaction at all. It did not, that reaction did not depend on B. It doesn't matter how much concentration of B there was, the reaction was going to be the same rate. So again, only reactants, and we have to figure out this M and N, these exponents, these orders of individual reactants experimentally. So again, you can use any letters, A and B, X and Y. It really doesn't matter. Those are just the exponents. Again, they're called orders for the rate law expression. So look over this. Hopefully you understand. Pause and reread it. But the reaction rate versus the rate constant versus the rate law. One thing I want to bring to your attention is the rate unit is always molarity per second versus the rate constant units are going to depend on the actual reaction order. So that's going to be really important later on because those units of that rate constant are going to differ depending on the overall reaction order. And the rate law equation, again, is that equation, that general expression that we have to figure out. So can you come up with a rate law expression for these two reactions? Think of A. Hopefully that makes sense. Again, here's our general formula. Rate equals RK, rate constant, times the concentration of our reactants to some order, to some exponent. We don't know what that is. It is not 2. It is not 2. It is not the coefficients. We have to figure that out experimentally. So can you get letter B? Again, hopefully that makes sense. And again, it doesn't matter what letters you use here, X, Y, A, B, it really doesn't matter. So give it some thought. Does this make sense? Hopefully you understood that, right? Second order, because that's the exponent for NO, first order for H2, and all together it's third order reaction. So what happens here? Hopefully that makes sense. Remember, when you're doubling the NO, it really is not doubled, it is squared. We want to remember that we are having it to that square, to the squared, and not that we're just doubling it because it's an exponent. Okay, so if we have a large K, that means it's a fast reaction. And if we have a small K, that means we have a slow reaction. So that should make sense, right? The larger the K, that means, again, we're multiplying everything. So we're going to have a fast reaction versus if we have a small K, that value is going to be a lower or a smaller. So it should be a slow reaction. That's not going to go as fast. So we want to remember that that rate law expression has to be determined experimentally, and the rate of reaction does depend on the concentration. The rate, how fast it goes, will depend on the concentration of our reactants, but the rate constant does not. Remember, that rate constant is going to be a constant for that particular reaction. However, it is dependent on temperature and the presence of a catalyst. Okay, see you in class.